We're going to continue on to the second part of homework 4, which is linearization. And we're going to start here with some of the equation matching, where we're trying to figure out what we should graph to prove the relationship between two variables, and also thinking about what the meaning of the slope is and the meaning of the y-intercept. So starting with question 1 here, we have the kinetic energy of an object is measured while the velocity is changed, and the mass doesn't change. So we haven't talked about kinetic energy yet, but we're given that relationship, K equals 1/2 mv squared. All right, so we're still able to do this problem. First, I'm going to think about what my independent variable is, and in this case, my independent variable is going to be that velocity. That's what I'm physically changing, and my dependent variable is going to be the kinetic energy. So we're going to start with our equation. We're going to isolate our our dependent variable. That's going to go on the y-axis, and we've already done that. K is by itself. Okay, and then we want to separate any constants from our independent variable, and we actually already have that. So this equation doesn't actually need any rearranging. So what I'm going to do is I'm just going to match it up here with y equals mx plus b, and think about what the meaning of all these things are. So my y-axis is simply going to be my kinetic energy, K. My x-axis is going to be v squared, okay, because that independent variable is squared, so we want to make sure we put that on our x-axis, because ultimately we want a line, we want a linear graph. My slope is going to be equal to 1/2 the mass, all right, because that's the constant that's in front of that independent variable, and my y-intercept is going to be equal to 0, because in this case I don't have a y-intercept. All right, moving on to the second one here. I'm just going to move that first one off to the side. The temperature of a room is measured in both Celsius and Fahrenheit. Okay, and for this one, we're going to take Fahrenheit to be the independent variable, and Celsius is going to be our dependent. We're given this initial equation that Fahrenheit is equal to 9/5 C plus 32. Okay, so we first want to rearrange this to solve for our dependent variable. So we're going to say that f minus 32 equals 9/5 C. Then I'm going to multiply both sides by 5/9 to get C by itself. And so I get 5/9 F minus 17.78 is equal to C. I'm going to now match that up, and I'm just going to change the order of this equation to say C equals 5/9 F minus 17.78. I'm going to match that up now with y equals mx plus b. So thinking about our graph here, the thing that's going to go on our x-axis is just Fahrenheit, and the thing that's going on our y is just Celsius. There are no squared, square roots, anything like that in this case. Thinking about our our slope, we look at that constant that's in front of our independent variable. In this case, it's 5/9. So this graph should have a slope of 5/9. And we think about our y-intercept, which is the part that's added on to the end of that side with our independent variable. And in this case, it is 17.78. So our y-intercept in this case should be actually negative 17.78. All right, and then moving on here to our final one, the resistance of a circuit is taken as the current is varied and the voltage is measured each time. So once again, we have another relationship, V equals IR, that we're probably not familiar with, but we will learn about it later in the year. So the resistance in this case is varied. That makes it our independent variable, the thing that we physically are controlling, while the current is measured. That makes that our dependent variable, right there. So now we're going to start with our equation here, V equals IR. Now I'm going to solve this equation for my dependent variable. So that means I. So I'm going to say V over R is equal to I. The other thing I'm going to do is, I'm going to put the I over on the left side instead. And I'm going to look here at this term, all right? V is a constant here. Okay, V is not a variable, and we want to always pull out all of our constants from our equation. So I'm going to say v times, and then what's left over? Well, that would be 1 over r. All right. So the reason why I'm doing that simply is to separate the constant from the independent variable. And now I can line that up with y equals mx plus b. Okay. And I can see here that on my y-axis, I'm going to have my current just by itself. On my x-axis, I'm going to have 1 over my resistance, so this would be an inverse function. And then my slope would be equal to v, that voltage, and we have no y-intercept because there's nothing added on to the end of it. Moving on to this next problem where we have to graph the data that we're given and then linearize that graph. I'm going to start out by making my scale on the x and y axis. And what I'm really thinking about is what is my range of values. So on the x, we're going from 10 to 100, and on the y, we're going from 2.5 to 7. So I want to think about that when I'm making my scale. So for the x, I'm probably going to say that every 2 lines is 10, and I'm actually going to zoom in on this graph to make it in a second. And for the y, I'm going to say that every 2 lines is 1 unit. So now I have my graph set up, and I'm going to go ahead and plot these points. Okay, I'm just going to do that. I figure at this point you guys should be pretty good with plotting points, but you can always check them with my graph once it's done. So once I go ahead and plot this, I end up getting some points looking like that, and we can see that that looks like an inverse function there. Okay, as x is increasing, y is decreasing, so an inverse function is a great idea for what that relationship is. So that means then that I'm going to plot actually y on my new graph. I'm going to plot y versus 1 over x. So we're first going to go ahead and fix our data points and figure out what our new points are going to be that we're going to plot. So here we are with my data table. I've gone ahead and done 1 over x for all of these x values. To calculate the new values I'm going to put on my x-axis, since we're going to have 1 over x on the x-axis to linearize this because it was an inverse function. And on the y-axis, it's just going to be the exact same values that I had before. There's nothing that needs to be done with those y values. So I'm going to go back to my graph here, and I'm going to plot these values now. Thinking about that scale, I'm going from, on the y, it's going to be the same. On the x, I'm ranging from 0.01 to 0.1, which means that I'm probably going to say that every 2 blocks is 0.01. So I've gone ahead now and set up my scale. What I'll sometimes do is, rather than marking off each individual tick mark, especially because it gets a little tight writing all of them, I'll just show what the first one is, and then I'll put my tick marks here to indicate, 0.02, 0.03, 0.04, 0.05, okay? And then I'll actually label that one, and then 0.06, 0.07, 0.8, 0.09, and then 1. So rather than having to write it out every single time, I'm just going to label some of those tick marks. But obviously it's up to you. You can do whatever you feel most comfortable with. So I'm going to go ahead now and plot these points. Just like before, I'll plot them, and then you can check them once I'm done plotting them. So as you can see, these points get fairly close together towards the end. That's kind of the nature of these inverse graphs. I'm going to draw my best fit line, something like that. And now that we have that here, we're going to go ahead and calculate our slope. So I'm going to look for some points. I tend to look for spots where it intersects nicely, and spots that are spread pretty far out. So there, I think, is a pretty good point. That's the point 0.09, comma 6.5. All right, now we want one kind of near the beginning. So this looks pretty close here too, although not exact. And that point is 0.005, comma 2.5. So I'm going to go ahead and calculate my slope, change in y over change in x. And so what I end up getting for my slope there is I end up getting a slope here of 47, all right, give or take. You obviously might have gotten a slightly different one depending on which points you picked. And then I look at my y-intercept, and it looks like we intersect right around 2 here. Okay, so I'm going to say that's my y-intercept, which means that the equation for this line is going to be y equals 47 times 1 over x plus 2. And obviously you're not going to get the exact numbers. The exact answer I had here was 50 for my slope and 2 for my y-intercept, but it's difficult to get that exactly when you're actually plotting these points. All right, moving on to our next linearization one. I'm going to start once again by thinking about my scale for this axis. So I see that my x values go from 1 to 10. So I'm probably going to say every 2 blocks is 1. And for the y-axis, we're ranging from 0.63 to 2. So I'm going to probably say that each one of these individual blocks here is 0.2. Okay. Just like last time, I'm going to set my scale and then go ahead and graph it. All right, and then we can check and see what that graph looks like. So I have my scale set here, and just like the last one, I'm not labeling each individual tick mark, just labeling some of them, showing like the halfway points and whatnot. I'm going to go ahead now and plot my points here. And I get a shape like this, which looks like it has a best fit line that looks something like that. Clearly some sort of an inverse function. So to linearize this, I'm going to start by doing 1 over my x values. So that's going to be what I put here on my x-axis, and I'm going to leave my y values alone. So let's take a look at what that looks like. So I'm now going to go ahead and do 1 over those x values on the x-axis and leave my y values alone. So let's take a look at what that looks like. So there we have my new values for our function. I just took these x values and did 1 over each one of those x values to get all these new x ones. All right, and then I left my y values alone. So I'm going to take these values now and graph it on my new graph. All right, my x or my y scale can stay the same. My x scale now goes from 0.1 all the way up to 1, so I'm probably going to say that every 2 blocks is 0.1. So I go ahead here and I plot my points, all right, using that scale that we just talked about. So we get some points that look like that right there. You might think that that looks like a relatively straight line, but if I do put a truly straight line on this, I see that that clearly is not a good fit for a straight line. Okay, it appears as though there is a definite curve to this shape. All right, something like that. And so that looks kind of like a square root graph. Okay, so I'm going to actually go ahead and linearize it again. All right, and this time when I come down to my graph here, I'm going to graph on the x-axis the square root of 1 over x and leave y alone. So let me go fix my points first, and then we'll come back here and graph it. All right, so now I have my final set of values here. All right, so my x values are going to be that 1 over, or the square root of 1 over x. My y values are just going to be y, those original values, and I'm going to plot this one last time, and we should be good here. This will happen every once in a while where you need to linearize it twice, okay, particularly when we're dealing with inverse functions. All right, so I'm actually going to maintain the same scale here on both axes, and I'm going to go ahead now and graph these new values. All right, and here we have our graph. We can see obviously that it gets a little bit jammed up in here. There's a bunch of points right in there with an x value between 0.32 and 0.41, so that's where it's getting all kind of jammed up. But we can still draw our best fit line from this. So our best fit line is going to be something like this. All right, that looks pretty good there. Okay, maybe we shift it just the slightest bit. All right, but there's a pretty good best fit line. We're going to go ahead now and find our slope. So I'm going to pick some points here. I see this point right here is a pretty nice intersection. So that's going to be the point 0.25 and 0.4. And I see another good point right here. And that's going to be the point 0.85 and 1.8. So I can go ahead and find my slope using delta y over delta x. So I get a slope here of 2.33. And for my y-intercept, I'm seeing a y-intercept that's actually a little bit below the axis. Okay, so I'm getting a y-intercept of negative 0.2 based on my graph. I see that these are slightly different than the actual answers given. And once again, that's just due to error, and that's going to be okay. Lastly, we could write the function here for this, so that function would be y equals 2.33 times the square root of 1 over x minus 0.2. Okay, and obviously if we were doing this in Excel, which is what we'd normally be doing, we're going to get a much more precise answer.